welcome everyone at our weekly colloquium. Our speaker today is my guest, Abraham Harte, who is an assistant professor at the Dublin City University in Ireland. Abraham is originally from the US. He did his bachelor in Caltech in Pasadena, and then his PhD at Penn State University, where he worked under Pablo Laguna on the topics of extended bodies and the motion problem in GR. He was later a junior scientist at the Max Planck Institute in Potsdam, and this is where actually I've met him for the first time. I was also a junior scientist at that time. And now he's an assistant professor. And he has worked on basically general relativity, very old and respected topics in relativity, the self-force problem and the theory of motion, and also on the electromagnetic and gravitational waves in curved spacetimes, and also on the nonlinearity in GR. So, Abraham, the floor is yours now.
Okay, thank you.
If you can share your screen.
All right, is that visible?
Yes. Yes, we see it. Mm-hmm.
Okay, perfect. Thank you. Okay, so I want to talk about extended body effects in general relativity and what is possible. So I'll explain what that means. And some of this work is together with a student, Michael Gaffney. So just to set the context for all of this, the basic question that I'm going to be addressing here is an ancient one, or perhaps one of the most ancient ones in all of physics, which is how do things fall in gravitational fields? And despite that people have been talking about this in one form or another for thousands of years, at least in a scientific sense or somewhat scientific sense, there are still some interesting things left in that direction. Okay, so how do things fall? So I'll start off with things that you probably know, so things that are in beginning textbooks. And well, usually we think of gravity from one of two perspectives, so either from a Newtonian context or from the context of general relativity. I'm going to be, in this talk, I'm going to talk quite a lot about Newtonian gravity just to sort of build up intuition for things, and then at some point I'll switch to GR, and the point of doing this is such that there won't be that much of a jump. So there'll be some distinction when you switch from non-relativistic to relativistic gravity, but for the most part, the concepts stay the same when you frame it in the right way. So okay, let's start at the beginning, and you go back to your first year physics or what have you, and you ask how do things fall in Newtonian gravity, and the usual way that this is described is that you have some gravitational potential phi, and then you say, okay, the acceleration of some object is just given by the gradient of that potential. So then you go to general relativity and you say, okay, what's different? Well, your sort of conceptual picture of the universe is very different. So you say that there's some space-time metric, G, which is dynamical, and then this determines for you some connection. And but in the end, you say that, okay, each object moves on now a geodesic of that connection. And the geodesic, so the connection is determined by the metric, and the geodesic, of course, is determined by the metric as well. And you have this kind of relation here. So you say that the object does not accelerate from the perspective of general relativity. And in some sense, this is actually simpler than what you have in Newtonian gravity, where you have to introduce an explicit non-zero acceleration. All right, but the point of these things is to look at them and say, okay, neither in the Newtonian case nor the relativistic one is there any explicit notion of the object's internal structure. So every object falls in the same way. There's no all you need to know is basically where the object is. So you have some notion of localization, and then you can, if you know where an object's initial position and its initial velocity are, you know its future and you know its past. So free fall is universal. You have this nice idea. All right. So in this talk, I want to challenge that, and I'm not challenging it in the sense of saying that either Newtonian gravity or general relativity is wrong in any way. I just want to say, I want to ask, is that really what these theories predict? And the short answer is not exactly, but usually they're very good approximations. Okay, so what happens in the Newtonian case? Well, you start with, so this is some object which is moving, and it's an extended object because all objects are extended. Point particles don't exist. That's perhaps a contentious statement, but I will stand by it. Or certainly if you're doing astrophysics, point particles don't exist. A star may look point-like to us, but nobody would claim that if you went right up to it, it would remain point-like. Okay, so we have some object like this, and we look at little bits of mass inside this composite body, and we say that, okay, each of them experiences some little force, and you could see that, well, the sum of these forces is going to be up and to the right, but clearly they're not all the same, and there's no reason, and to sum all of these up, you really have some integral. So you say that the acceleration of the body as a whole is given by, well, you sum up these gradients of the potential in a way that is weighted by the mass density of your object. So if most of the mass was weighted up here, then, well, this one is going to matter much more than this one. Okay, so if you look at this, it seems like there is a dependence on internal structure. You have this mass distribution here, and different objects will have different mass distributions, so perhaps they do accelerate differently. And you could ask, all right, when is this actually equal to the thing that we had before, just the gradient of the potential evaluated at the center of mass? And well, the first question to ask is, when is it exactly equal to that? Well, there are a couple different things you could say, but it turns out to be exactly equal if your object is spherically symmetric. Right? So if this blob were a sphere, then this integral collapses exactly to this gradient of phi, and that's it. There's nothing else to say. But not all objects are spherical. Of course, most things that you look at in astrophysics are close to spherical. So usually that's one reason why this is usually a good approximation. There are other reasons as well. But let's see what else happens. So let's look at if you actually try to expand that integral in some sort of sense where this term comes out at first order, then what do you see? So there are actually two categories of corrections that you need to make. The first category is kind of a subtle one. So it says that, well, I need to add this little subscript here. And what this is saying is that you should not be using the actual field gradient at the center of your body, but you need to construct a field gradient of just the external potential, just the potential that's created by everything except the body that you're interested in. So this is a non-local operation. So you can't just sit in a neighborhood of the center of mass and compute this thing. You really need to know the entirety of the object that you're interested in. And the reason for this is due to self-interaction effects. So the fact that bodies create self-fields and these interact. But okay, this is not something I want to focus on in this talk. So that's just some correction to the first term. The things that I want to focus on are the additional terms that you also get. And these are what I'll call extended body effects. So the first extended body effect looks like this. So this looks a bit complicated, so let me explain it. This is basically a multipole expansion. So the first term here is the monopole. There would in principle be a dipole term, but that vanishes when you choose Z to be the center of mass. And then in the next order, you have a quadrupole, then you have an octupole, and so on forever. And every time you do this, you get another derivative of the field that couples. So here you have one derivative. A dipole would have two if you didn't have a zero in front of it. And then a quadrupole has three derivatives, then an octupole would have four, and so on. But the interesting point here is that you have now introduced some new parameters that describe how this object moves. And these parameters are what you call its quadrupole moment, which is here a rank 2 tensor. And this rank 2 tensor depends on the internal structure of the body. So you need something to kill these extra indices, these J's and K's, And that is these particular pieces of information from the internal structure. So now so once you go to this level of approximation, different bodies fall in different ways. And this is the end of the equivalence principle. So if you want to, you can define an equivalence principle so it's exactly true by just putting in enough if statements, or alternatively, you can say that it's an approximation to the full result, and this is where it breaks down from that latter perspective. So free fall is not universal. Okay, so what do these kinds of effects look like? So if you have your orbiting body out here, again, this green blob, and you say, let's say you're orbiting around the sun over here, your distance r from the sun, your green blob is of size of order L. So these extra effects here turn out to be of order, basically the ratio of these length scales. So how large is the object compared to how far away is it from other things, quantity squared. So this ratio L over R is usually, in most astrophysics problems, very small. L over R squared is, of course, even smaller. So usually this term is tiny, which is why it's not discussed very often at an elementary level. But it is there. It actually has some important astrophysical consequences. So this talk is not about astrophysics. I'm just sort of connecting a little bit in case you're interested. But so you have tidal effects, for example, are all of this form, and you have tidal locking of the moon to the Earth, for example, and this is also related to the distance between the moon and the Earth secularly drifting over very long time scales. So all of these kinds of things come from this sort of term. But the important point is that you have these internal parameters, and these are of order, basically the mass of the object times the square of its size, or that's the largest they can be. So to be a little bit more specific, the quadrupole moment is really just it's just some characterization of the mass density of the object. What is its mass distribution? You're taking the second moment of that mass distribution in the sense that you would do in statistics. And well, there's this little bit that you want to take the trace-free bit of that, which is not really very important. And if you don't know where that comes from, just accept it as something that's there. It doesn't really matter. But the important point is that, okay, the components of this are a 3x3 matrix. It's a symmetric matrix. You can see it's a trace-free matrix. So, okay, symmetric 3x3 has 6 components. Trace-free kills a component. So you have 5 components here. And that means that, okay, you have your extended body has an uncountable infinity of internal degrees of freedom in principle. But in order to describe motion at sort of the first non-trivial level of approximation, you need only 5 numbers. So you take that infinity of possible things that you could construct, and you have only 5 numbers that you need. Okay, and one thing that is quite crucial for the rest of this talk is that the time dependence of this quadrupole moment is not constrained by any universal laws of physics. So if you have some microscopic description of your object, so say it's some self-gravitating fluid ball or whatever, you could, write down initial data for your fluid equations and evolve it, and you could compute what Q is as a function of time. But if you take some completely different sort of object, it can have a completely different time evolution. So for example, I can wave my hands around, in whatever time dependence I like, and I can change my quadrupole moment. And I can do this, I can make the time dependence of my arm waving anything that I want, up to limits of how quickly I can wave my arms. And that means that I can make my quadrupole moment be any function of time that I like. And there are bounds because my arms are only so long, so I can only make Q so big, but the time dependence is arbitrary. So this means that if we wanted to imagine that we could build an object, build a spacecraft, let's say, we could engineer this spacecraft to have Q do whatever we want, up to some bounds given the size of the object, but we could make it control its Q. And if we control the Q, we can control sort of the force that's acting on the object, and perhaps we can control its motion. So this is what I want to focus on. But once again, free fall is not universal. Different objects will have different quadrupole moments. They will fall differently. Okay, so this is this is kind of the idea that I was just hinting at, and it's sort of a central question of can an object control its orbit by controlling its shape? So if you have some spacecraft and you're stuck in orbit around something, and you've run out of fuel, you can't use your rockets, are you stuck? Can you possibly get home? And perhaps the surprising answer is that you're not necessarily stuck. You might be able to get home. Now, you have to be very patient usually, but it is possible. So this is this kind of whimsical drawing is not actually taken out of a random place, but is actually talking about exactly this this problem. And the idea here is that you have some spacecraft, and you have a mass at the end of an extendable tether, and these sailors up at the top are reeling in the tether or letting it go out, so changing the length of this rope. And as they're doing that, they're changing the quadrupole moment, they're controlling it, and if you control this in the right way, you can do interesting things. Okay, so what can you do? And what I would like to...
Excuse me, can I ask a question?
Yes.
I just, by accident, have come about an article of constructing satellites, and I think this, what you are talking about, has been considered already. An extended satellite experiences a torque depending on distribution of its mass, and whatever it means improbable, the slight difference of gravitational field of the Earth due to its dimension, so to speak, makes it necessary to design it carefully somehow, so it does not behave in an unpredictable way.
Yes, that's correct. So these effects have been known. Well, these effects have probably been known for hundreds of years. I mean, at least the governing equations, and the fact that they relate to spacecraft motion definitely has to be taken into account in terms of especially torques. So this is kind of a standard thing for people who are engineering these spacecraft. Now, in terms of actively controlling orientation using these effects as opposed to just sort of trying to avoid problems, that's also been discussed for quite a while, but and there are some limited applications that have already been produced, but not so much. In terms of more translational control of, can you not only just control the orientation of your spacecraft, but also control which orbit it's in. That again, there are some results on this that go back to the well, some Russian publications by this person Beletsky back in the 1960s at first. There's actually quite a lot of literature that's also incorrect on this, but yeah, it's been building up and people know about it, although there haven't been so many applications in that direction yet. That's right. Okay. Right. So I think this is not a very well-known topic, so I'm introducing it from the beginning as much as I can. Okay. So I have this question: can a body control its orbit by controlling its shape? And so you can have this control in terms of sort of rotational control. Can you control your orientation? And there's also a control of, can you go from one orbit to another? And I want to introduce this by starting with not sort of saying you can do this, but rather saying you cannot do this, something else. So I want to start by saying what you cannot do using these effects. And then, as is often the case in physics, you can do pretty much anything which is not forbidden. Okay, so what is forbidden? You're forbidden to do things by symmetries. So if your system has some sort of symmetry in it that's going to apply a conservation law, and no matter what kind of clever mechanism you have in your spacecraft, that mechanism will not be able to violate that conservation law. and that will prevent you from doing certain things. Okay. So what are some examples of this? Again, still in the Newtonian context. So let's start with the simplest possible example of you're sitting in a homogeneous gravitational field, and you then have all 6 Euclidean symmetries, Euclidean killing fields to be more precise, are going to be symmetries of your gravitational field. So all of your 3 translations and 3 rotations will preserve the relevant structure. And what that's doing is that will give you 6 conservation laws, and that will completely fix your 3 components of force and 3 components of torque. And in that case, that means that there's no maneuvering that's possible. There's no freedom to break out of those conservation laws. So you can't do anything interesting in a homogeneous field. That's probably not surprising. Okay, so then the next perhaps interesting case is to look at a spherically symmetric field. So you're in orbit around the Earth, let's say, which is close to spherically symmetric. There are then 3 symmetries for the 3 rotations. And that will give you 3 conservation laws. It gives you, it fixes 3 out of the 6 force and torque components. So you still have 3 left over you can do something with. But the end result of that is that your angular momentum has to be preserved. You cannot use extended body effects to break this conservation law. That's what you're forbidden from doing. So you can, for example, change your orbital angular momentum L, but in so doing, you must take that angular momentum and spin yourself up. Okay? There's no way to avoid this trade-off between orbital angular momentum and spin angular momentum. Okay, if you now have an oblate gravitating mass, for example, then you just have axisymmetry. You just have this one direction of one rotation. So now you have really 6 minus 1, only 5 force and torque components are still free. And in fact, you don't have angular momentum in general is not conserved, but just one component of it is. And this means that, for example, you can change the inclination of your orbit without spinning yourself up. This is something you can't do in spherical symmetry. Okay. So these are the things that are forbidden. And the kind of intuition for this is that in order for any of this to work, you kind of need some gradients to grab onto. You need the field to be changing. All right, so what happens now let me switch a little bit and say, okay, that was all Newtonian physics. Now let me go to GR. And I don't want to go into great detail about what changes when you go to GR. I just want to point out a few little differences. So the theory of extended body motion in GR was, well, there's a complicated history, but let's say the beginning of the road which led to the understanding was started by Matheson in the 1930s, and then he died very young, and the war happened and so on, and that was forgotten for a long time, and then it was taken up again by to simplify the history, by Dixon, who completed this work, if you like, in the 1970s. And he was able to understand how all extended body effects work in GR to all orders. Originally, this was without self-interaction, and this has since been fixed or incorporated. Okay, so what happens? I don't want to go into the details again, but I want to say, okay, you have some, let's say, translational degree of freedom. So you have a linear momentum, which has some evolution equation. You have some angular momentum, which has an evolution equation. You also have these things in Newtonian physics, but here it's a little more complicated because you have, for example, a spin curvature coupling, which shows up in here. Okay, fine, it's whatever it is. But now something which is different, you don't have in Newtonian physics, is that the relation between momentum and velocity can be non-trivial. So in Newtonian physics, this relation is sometimes viewed as a definition, that the momentum is proportional to the velocity of an object. It's not a definition, that's something that's derived. So you have a definition of center of mass, you have a definition of momentum, and you then show in Newtonian physics that this relation is satisfied. Okay. In GR, you have to do the same thing. So you have to start with the definition of center of mass, and there's a long story with that I don't want to get into. You start with the definition of momentum, and you then try to see how these are related. And in general, you don't just have this, but you have something extra. In fact, you have this also in electromagnetism in flat space-time, where this is where this term originated, that it's called a hidden mechanical momentum. So there's some extra component to the momentum that's not just due to the center of mass motion. Okay, so that's a non-Newtonian effect. I'm not going to talk any more about this. I'll just point out that it's there. And one also has extended body effects. Just as you do in Newtonian physics. Of course, anything in Newtonian physics has to also be there in relativistic physics in some form or another. So you have, let's say, a quadrupole moment, and this corrects the lowest order motion, which is this geodesic motion. So objects don't move exactly on geodesics, but this is corrected. And one thing that happens that's kind of interesting to point out is in Newtonian physics, you have a quadrupole moment that it's a rank 2 tensor, because you're describing the second moment of a scalar, which is the mass density. That's because in Newtonian physics, only the mass density couples to gravity. In GR, the whole stress energy tensor couples to gravity. So you end up with 2 more indices here, and your quadrupole moment now has 4 indices instead of 2. So it looks unpleasant. But in fact, this thing has the same algebraic properties as a Weyl tensor. So it has 10 components, which compares to the 5 components of the Newtonian quadrupole moment. So you have it seems like twice as many things to worry about. But you can split this into two parts. So you can split this into kind of a normal Newtonian looking mass quadrupole, which is symmetric and trace free and has 5 components and looks basically in this form that I had before. Okay. But then you also have this new thing, which is what you often call a momentum quadrupole or a current quadrupole. This is also symmetric and trace-free. It also has 5 components, and this is sort of a second moment of the momentum density. So you have sort of a rho times an internal velocity, roughly speaking. All right, but the point I want to emphasize is just that that you have something extra coming in GR. All right, so all of that. Sorry, all of that says that GR looks much more complicated. The theory of extended body motion looks more complicated. You have well, more complicated equations for the linear momentum and the angular momentum. You have this, in principle, hidden momentum effect. You have a quadrupole moment with many more components. It looks like it's going to be a horrible mess. But it turns out that if you look at things in the right way, at least within the right regimes, and I don't mean sort of a Newtonian limit, but I mean really just sort of looking in certain parts of parameter space, it's almost identical to the Newtonian problem. And I want to focus now for the rest of this talk on something specific. So I want to say, suppose that you have a spacecraft or some controllable body, let's say, that is in the Schwarzschild space-time. So we have a black hole, spherically symmetric black hole, and you're looking at orbits around this black hole, and you're saying, what is possible for extended body effects? Can you do something? Can you change your orbit without using a rocket, just by manipulating your internal structure? And I want to specialize now. I want to say, okay, let me look in a case with no spin and no torque to make life easy. It's not only to make life easy, it's also to prevent yourself from spinning, let's say, spinning yourself to destruction. But this also makes the analysis much easier. So I want to say, okay, actively control your quadrupole moment in order to ensure that there's no torque on the body. This is not something that happens generically. You need to actively control your shape in order to do this. So that's step 1. And step 2 is, all right, if you have any freedom remaining to still manipulate your shape, use that to control your motion. All right, this is possible. So I said you start with 10 quadrupole components. It turns out that 5 are irrelevant. You need to control 4 of them to fix the torque. And so now you have 10 minus 9, you have 1 component left over. that one quadrupole component can be used to control your motion. All right, so what does this motion look like? It turns out that it's governed by basically the effective, the radial component is basically determined by effective motion in a one-dimensional potential of a non-relativistic body. And this looks very much like a textbook description of geodesic motion in the Schwarzschild spacetime. I'm not talking about geodesics though, I'm talking about extended bodies. But, so we have this effective potential here, which looks like this, which has the usual features of the effective potential in Schwarzschild for geodesics. But now I'm saying this depends on not only a radius, but also on a mass. And if the mass is constant, this is actually exactly the geodesic expression. It's identical to its point particle counterpart. Okay, so are we doing anything? Are we actually changing anything? It turns out that all of the effects of all of the extended body effects in this context come in from the fact that this mass is not necessarily constant. So by controlling the quadrupole moment, you can control the mass. And by controlling the mass, you control the motion. Okay. So in fact, you can write down, all right, a little bit of a change in mass is related to, so J is your free component of the quadrupole moment that you can vary. But a little bit of change in quadrupole in mass is determined by a little bit of change in, this is basically a component of the curvature. And the conversion factor between changes in mass and changes in curvature is going to be this quadrupole moment, which can be of either sign, depending on how you configure your object. So this might seem exotic that you're changing mass, but in fact, it's a common thing whenever you're looking at extended body effects relativistically. So even if you go into your kitchen and you take a couple of magnets off your refrigerator, and you let one accelerate the other. So you learn in first year physics that a magnetic field can't perform work on a charge, but clearly you can accelerate a magnet with another magnet. How is that? Well, if you analyze it properly, it turns out that the kinetic energy, so now you have dipole interactions. These are extended body effects, if you like. And the kinetic energy of the magnet is coming from the rest mass energy, if you like. All right. So this is just another, a more exotic example of that. Okay, so we have this relation. So again, control the mass, you control the motion. So we want to control the mass. How do we do that? We start with this relation, but it turns out it's useful to define a different mass. So it's useful to subtract off something that's like the quadrupole potential energy. So this is, if you think of this sort of with some kind of vague thermodynamic analogy, this is kind of like, an ordinary energy and a free energy or something like that. And we define this thing as some kind of effective mass. Of course, if you know one mass, you know the other one. So they're equivalent. But the nice thing about this expression is that changes in this mass depend only on changes in your quadrupole moment. This depends on changes in your curvature. Okay, so why is that useful? Well, again, think about this sort of like a thermodynamic process that you, the only way you're going to get a large effect out of this is if you wait a long time. So usually J, the quadrupole moment, is something small. So whatever change in mass effect you might expect would also, you might expect to also have a small change in mass. But okay, if the thing just is slightly different than geodesic motion, who cares? The interesting point is to say, over a long time, you can have a large change in mass and therefore a large change in orbit. Okay, so in order to do that, we say, let's cycle the object. So we cycle J back and forth. And if we cycle J back and forth, what we want is to say, as we repeat one cycle in J, we do something to the shape of the object and then bring it back. We want to say that after that one cycle, the mass has changed, right? The quadrupole moment has come back to the same state, but the mass is different. And if we then repeat the cycle many times, even if the change in mass over each cycle is small, you do many, many cycles, you can get a significant mass change. And if you think about this a little bit, and you draw sort of a diagram here with quadrupole moment on one axis and curvature on the other axis, one of these cycles looks like some path in this plane, and the change in mass over this cycle is the area enclosed. So as long as you design a cycle with some non-zero area, you can raise the mass or you can lower the mass. And you just repeat this over and over, and you get larger and larger changes. Okay, so what does that do? What can you do with that? Suppose that we're changing the mass. What you can think is that sort of on each orbit, you're approximately moving on a geodesic, right? But over many orbits, you can perhaps change the mass significantly. So your approximating geodesic might change considerably from early times to late times. Okay, so you can imagine that your motion is basically drifting through the space of approximating geodesics. And you can now, this is now a plot of the space of geodesics, so parameterized in a particular way. So we have here an eccentricity and a semilattice rectum. So these are concepts from Keplerian motion, but you can generalize them to the relativistic motion in Schwarzschild, and they parameterize the geodesics. And now each line here is what happens to the geodesics as you change the mass. So a particular spacecraft of the type that I'm describing sits on one of these lines. And if it increases its mass, it moves to the left. If it decreases its mass, it moves to the right. Okay, so I will explain in more detail. Okay, the first thing that you get from this is that if you increase your mass, you're going to the left, and whichever line that you're on, you're going to go down to here, to the vertical axis, which is eccentricity 0. So those are circular orbits. In fact, these are the stable circular orbits. So these are with radii 6m or greater. So if you increase your mass, you take an eccentric orbit and you make it circular. Okay. Decreasing mass is more interesting. So let me put that here. There are two possibilities. So if you're on one of these blue curves, decreasing mass means move to the right. If you move to the right, you keep moving to the right, you're decreasing, decreasing, decreasing. Eventually you come here. You're at eccentricity 1. This is an unbound orbit. That means that if you start on a bound orbit and you perform these maneuvers, you have these cycles with non-zero area, eventually you unbind your orbit. You're stuck around the black hole, and you do this operation, you eventually can make yourself escape. So you're not stuck if you run out of fuel. Okay, but that's only if you're on one of these blue curves, right? So you need to be above a certain threshold. You need to be above here. And if you start on a circular orbit and you try to escape, you can characterize this by saying that the radius has to be greater than this boundary here, which is given by about 10.5 times the mass of the black hole. Okay. Now, what if you're below that? Well, then you have to worry about this gray region that I didn't mention. So this gray region is where these parameters no longer make sense. So if you like, it's the separation between stable orbits above and unstable orbits below. And this line that is on the boundary is called the separatrix. So geodesics on that line are going to asymptotically approach unstable circular orbits. So even if you're at high eccentricity over here, a point there is asymptotically approaching a circular orbit with radius below 6m. So if you're on one of these red curves and you decrease mass, you're eventually going to run into this boundary. You run into the separatrix. And that means, at least formally, you're going to be approaching one of these unstable circular orbits. But in fact, you have to be a little bit careful there because, as I said, these orbits are unstable. So if you're not very careful in how you do this, well, you're not going to be exactly on one of these orbits. So you're going to excite the instability and you'll just fall into the black hole. So if you're above some threshold, you decrease the mass, you eventually escape. If you try to do the same thing and you're below that threshold and you're not careful, you'll actually make yourself fall in. So there's this, you know, sort of complete freedom or complete death on this side, and this is the dividing line. But if you're careful, you can actually do something else. So you can use extended body effects to also stabilize your motion. So you can have a control mechanism, and you could take in feedback from what's happening and adjust your quadrupole moment. And to do that, you can actually get to this unstable circular orbit, and you can sit there stably using these extended body effects. So you don't have to plunge. Okay, so here's kind of a complete example that's a bit fun, I think. So what I'm illustrating here is you're using extended body effects to move from one circular orbit to another, and this is only possible in the strong field regime where you're on one of these red curves. So if that's true, you can start from a stable circular orbit on the vertical axis to an unstable circular orbit on the separatrix, or vice versa. There are only, for a given body, there are only two possible circular orbits you can go between without introducing torques. If you introduce torques, you can do other things. There are only two circular orbits you can go between in the strong field regime. If you're not in the strong field regime, if you're up at the top, you can't do this. You can only be in, there's only one possible circular orbit. But all right, otherwise you can transfer. So here I have a transfer from a 5M orbit. So that's unstable. That would be an unstable geodesic. To green is 7.4 M. And okay, this is the plot of radius as a function of time. And we have here, we're starting at 5M. As I said, this is an unstable orbit, but I'm applying a feedback regime that gives me stabilization using extended body effects. So you could see you're sort of oscillating a little bit about 5M. So you've stabilized the instability. And then when this changes color, I turn off that stabilization mechanism, and I change the quadrupole moment a little bit to, well, you can take advantage of the instability and either kick it into the black hole and, well, kill yourself, or you kick it out of the black hole. And so I've kicked it away from the black hole, and you go into this orbit, which now looks very highly eccentric. So if you go into this diagram, so, all right, we're ending up at 7.4 M here. So we trace it back here. We're basically on this curve. So we start off on the separatrix here, and I kick it immediately off. And so we have something of an eccentricity of 0.4, 0.3, something like that, which is what you see here with this blue curve. And then what I'm doing is I'm applying this one of these mass increasing cycles. So one of these cycles with non-zero area. And as I do that, the amplitude of these radial oscillations decreases because I am, again, moving to the left here. I'm decreasing the eccentricity by increasing the mass. And eventually I'm coming all the way to the vertical axis, and I've come here, I've gotten myself a circular orbit. And for the green portion, I've just turned off the quadrupole moment. I've set that to 0, so this is a free geodesic. And this is now a stable circular orbit, so it oscillates a little bit. You're not exactly on it, but it just stays that way forever. So you have this sort of complete maneuver that you can design. All right. So I think I will skip that last slide and just go right to my conclusions. So to summarize all of this, I mean, this is kind of a, if you like, fun problem, but it sort of indicates sort of what is allowed by the laws of physics. And you might wonder, well, what does this imply for the, what are the possible motions of naturally occurring bodies as well? Of course, they're not going to be as extreme as the things I was talking about, but you can get less optimized versions of these effects that might occur in nature, or can occur in nature in some cases. But the basic idea is that, even though you have this kind of idea of an equivalence principle, it's not exact. And these extended body effects can allow bodies to control their motion without rockets, just by internally rearranging themselves. And you can have quite dramatic effects. You can have large mass changes. And from that, you can have bound orbits can be made unbound. You can stabilize unstable orbits. You can do other things as well. And all of the things that I discussed are just in the context of spin-free, torque-free bodies, or at least the last part of the talk was spin-free, torque-free. And once you lift those restrictions, you can do even more. So I think there's a lot of detail and kind of interesting questions you can ask about what can happen for extended body effects in GR. Okay, and if you want to read more about this, so Michael and I wrote a paper on the Newtonian version earlier in the year, and then there's a paper on the GR version of this, which came out on the archive yesterday. Anyway, thank you.
Thank you very much for a very interesting talk, Abraham. I would like to ask if anyone has a question. Please raise your hand or ask.
I have a comment. Jerzy Kijowski. May I?
Yes, sure. Go on, Dr. Kijowski.
The entire idea is based on the conviction that turning on engine costs money, whereas changing the shape does not cost anything. You are waving your hands to show us that we may freely change our shape, but this is true only when the field is relatively homogeneous. But this is precisely not true because to use your effect, you have to use non-homogeneity of the field. And if the field becomes really non-homogeneous, then waving hands becomes very costly. So I don't believe in practical effects. Whereas, of course, mathematically, this is a nice, everything turns on. Roughly speaking, you cannot treat the rocket as a purely passive, something which is purely passive, because those elastic forces which you need to change to move the parts of the rocket are not taken into account. So it is.
Yeah. Yes. So so you're certainly right that this requires energy, and indeed that's kind of the point, that you're able to use internal stores of energy in order to maneuver. But the other part of the point is that you don't need to eject any part of yourself to do this. So you don't need to have actual material that you throw away, that you may run out of, as you do with an ordinary rocket. So, I mean, whether you call one, whether you decide that one is a cost or another is a cost, I mean, you could have solar panels on something and you have kind of an unlimited source of energy in that sense, whereas you don't have an unlimited source of rocket fuel. But anyway, your point is correct, that that you do have to exert energy, you do have to expend energy to do this.
Thanks for the reply. I've got a very much related question. So if I may ask it right now, I understand that even in the case of the case of Schwarzschild method, you always have the conservation of energy because of the time symmetry. So it should be possible to see this type of this need of applying work in order to change your orbit. It should be actually, it's fairly easy to quantify how much work you have to use.
Yes, yes, indeed. So it's actually quite interesting that you have a conserved energy, indeed, but you do not have a conserved mass. And if you like, the energy for changing the orbit is coming from the rest mass energy, and not from the total energy.
Are there any more questions to Abraham?
I have a question.
Yes, please go on.
So I just wanted to ask you if you could elaborate this problem from a non-holonomic point of view, because as far as I see, you have want to control some motion. So that means you have a configuration space and some parameters that you control, and then that means you have a because you're saying that it's controllable, that means you have a distribution, some sort of distribution that is non-holonomic, so packet generating, and it allows you to control. So if you could elaborate what exactly, I mean, you probably have said it implicitly, what this configuration space is, what dimension is it, what are the parameters, and what's this distribution, the rank of it, and the growth vector, these sort of...
Okay, so I may not be as specific as you would like, but in this regime where you are in this spin-free, torque-free regime, which is this very specialized case, then there's only really one parameter that you can vary, which is this quadrupole moment J, but then sort of your natural motion of the object is changing this this curvature, and so if you control J in some path in this space, I mean, kind of in the way that you were saying, then you will have a non-trivial effect. Again, once you start introducing, once you lift the torque-free assumption, then you have 5 parameters in total that you can play with. And one of the interesting things that you can do is actually, so you can't do this in the case where I was discussing, but if you lift the torque-free assumption, so even if you keep the 0 spin, you can still, you can add extra control here, and you can sort of directly control your velocity rather than just controlling your, let's say, acceleration. And this is an unusual kind of effect, but otherwise 5 parameters. I don't know if that completely answered your question.
Okay, yeah, thank you.
I'm not so sure that my comment.
Yes, please go on, Professor Turski.
I'm not so sure that my comment is fully within the scope of your lecture, but years ago when I was busy with the problem with dynamics of traffic control, and I read this story about the fact that the trucks with the rigid structure of the containers they are towing behaves very different when they hit the curb and they turn over than the same truck with the elastic soft cover of the thing, so the shape is changing. And more related to gravitation field effect is tall buildings in the earthquake-prone regions of the world are built up such that they have a very heavy movable objects on top. And the motion of these heavy objects on the top, which used to be a swimming pool or a very heavy metal balls like in this tallest building in Taipei, then they move, and that they control the motion of the whole building within the gravitational field, which is homogeneous, though for the curvature of the surface of the Earth is irrelevant for most of the purposes of the earthquake dynamics. So I'm not sure that somehow this controlling the motion of an object by changing the shape is very old problem in physics. The ballerines and the ice skaters use it every day by performing. So
yes, so sorry. Yes, so in your example of a building with a mass damper in it, then you don't have only the homogeneous gravitational field, but you also have, of course, the foundation, which is acting on the body, and it's the interaction between these two things that you're controlling. And you know, as you say, people have considered these sorts of things for many years. But it's a little bit different if your only forces are gravitational. Then in a homogeneous field, you can't do anything.
Okay, thank you very much for the answer. let's say we have time for the final question. Is there anyone?
I have understood a comment by Jurek Kijowski that the more inhomogeneous gravitational field is, so the easier is to use this effect you have discussed. It's also more difficult to shift masses around your body, and it costs more energy. So there is some kind of feedback loop, which makes this more difficult.
Yes, you have to work against the tidal flow.
Simply means that maybe it is easier to turn on the engine.
Yeah, of course. In normal situations, it is. Yeah, that's right.
Anyway, you have to turn to move the pieces of the engineering construction with respect to each other. I mean, how can you change the shape of a? I mean,
so you have a tether with a mass on it, and you could extend and contract the tether.
but in order to extend the rope, you have to apply the force. So you have to have an engine.
Of course.
And
but you don't need to extend.
The engine is a mechanical device by itself, which has a certain extension. And from the point of view of a gravitational field, it's a different object when it's moving or not. Because if the wheel is turning in the gravitational field and the forces applied to it are not homogeneously distributed, if they have to change the shapes of something with respect to another, then the whole thing is extremely complicated and is enormously energy consuming. This is why the space station is rigid. The space station, which is the huge giant satellite, which has to be stabilized in a very complicated way on the orbit, is rigid structure. It doesn't position itself on the orbit by moving its part with respect to each other.
Yes.
Well, it's anyway rusted, so if you do remove the parts, it will fall apart.
Okay, thank you very much for the comments and questions. I think it's time to thank our speaker.
Absolutely.
I think it was a very nice lecture.